Today I'm continuing my series on solving some of the hardest mathematics exams from across the world, and today we're looking at the University of Cambridge's mathematics entrance exam. Let's dive straight into it. Essentially, if you want to apply to study mathematics at the University of Cambridge, then you typically have to take what are known as the STEP examinations, and these stand for the sixth term examination papers. Now, there used to be 3 STEP papers, so Step 1, Step 2 and Step 3, and as of 2020, the Step 1 paper was actually discontinued. So typically students that are applying to Cambridge have to do Step 2 and Step 3, and that is alongside their A-levels or equivalent if you're studying not in the UK. So yeah, it's pretty intense, and we're going to look at the STEP paper today. Now, I have chosen to do the Step 1 paper from 2017, despite it being discontinued now. The reason for that is because the maths in it is typically quite nice. I realise that when I make these videos, I want people to understand the maths that goes behind it. So I picked 3 questions from Step 1 that we can explain, we can go through, which is what I'll be doing in this video, and then I'll be making other videos on Step 2 and Step 3. So essentially I want to give you 3 different videos where you can see the progressing difficulty in the STEP examinations. And the first thing we're going to do is look at the exam, look at what it entails, and then we're going to pick 3 questions from Step 1 of 2017, and I'm going to walk you through the maths in them. So without further ado, let's dive straight in. Okay, cool. So you can see that this is the STEP paper, which we can see here. It's a 6th term examination papers. This is Mathematics 1, so it is the STEP paper 1, and like I said, it's from 2017. And immediately we can see that the time for this exam is 3 hours. So students have to sit, and I believe Step 2 and Step 3 are also equivalent. So yeah, these exams are pretty long. Okay, cool. Now let's look at some information about the exam itself. So this is just instructions to candidates here. So this is basically if you sit in the exam itself. And then this is the stuff that we're wanting to look at. So each question is marked out of 20. There's no restriction of choice. So essentially you can answer any of the questions in the exam. All questions attempted will be marked. So you could theoretically answer every single question in this exam and they will be marked. But it says that you are advised to concentrate. So here it says you're advised to concentrate on no more than 6 questions. And again, it says your final mark will be based on the 6 questions for which you gain the highest marks. And again, little credit will be given for fragmented answers. So the idea is you would sit the Step 1 exam, and you would want to focus on 6 of the questions in it. Okay. So before I show you the 3 questions that we're going to look at today, let's look at the entire paper. Here's section A, and it's on pure mathematics. This is question 1, which we're going to focus on today. This is the whole of question 2. This is question 3. And feel free to pause the video if you want, maybe give the questions a go yourself, and yeah, see what answers you get. This is question 4. This is question 5. All of this, if I zoom out, is question 6. Again, all of this is question 7. This is question 8. And then we move on to section B, which is on mechanics. Lovely bit of mechanics. We have question 9 here. We have question 10 here. Then we have this very wordy question 11. Then we move on to section C, which is probability and statistics. And this is an entire question 12. And then this is the entire question 13. And I think, yeah, that's it. So there are 13 questions in total, and I believe that was the same for all of the STEP papers, Step 1 papers. Let's dive straight in, and the first question we're going to look at is question 1. So the first question says, and it's a really nice question really, it just says use this substitution to find the answer for this integral. So this is the first bit that we want to do here. I wrote down the substitution that we want, so it says u equals x sine x plus cos of x, and that's what we have here. And the first thing I did was find the derivative du by dx. And so when you differentiate this here, you have 2 x's. We have 2 terms in here, so we have x and sine x. And so you differentiate the first and leave the second alone, so we get sine x. And then we do the same, but leave this alone and differentiate this, so we get x cos of x. And then we can just differentiate cos of x, which we know is minus sine x, which is what we have here. And then these 2 cancel, And so we are left with x cos of x. Okay, cool. And then all I did was rearrange this here so that we know what dx is. So I got this for dx, and the reason for that is because we'll want to substitute it into here. Okay, so the first thing I did was substitute the dx. So we substituted dx into here, and we get this here. Doing a nice bit of rearranging, I essentially just cancelled this x with this x, and then moved the cos over to the front of here. So we get this here. Rightly, we know that tan of x is sine of x divided by cos of x, and so we can simplify this here because cos of x multiplied by x tan of x here is just going to be x sine x. And then we have plus cos x because we have 1 multiplied by cos x here. Amazing. And rightly, we know that u is x sine x plus cos x, and so this just simplifies to this really, really nice integral here. Amazing. And so, yeah, we can integrate this and we get, it's the natural log of the absolute value of u plus c, not forgetting your constant there, that's something that was drilled into me by my A-level teachers, plus c, and we can then just simply substitute the value for u in here, and so we get this final equation here for the integral. Amazing. So let's look at the second part of the question. Now it says, find by means of similar substitution or otherwise, and we're asked to find this integral. We can see that this integral here and this integral here are very similar. All it is that we have a tan x here, but we have a cot x here. And obviously we know that cot x is 1 over tan x. And so what I kind of deduced from looking at this straight away was that we're going to have a very similar substitution, but the substitution is going to vary slightly just so we have a 1 over tan x here rather than tan x. And the very nice substitution for that is just this here. It's very similar to what we had before, if I can just find what we had before. So we had x sine x plus cos x, whereas here we have x cos x minus sine x. And essentially what you do is when you figure out that's the substitution for this here, we do the exact same thing as we did before. We compute du by dx, we substitute it in to here for dx, and then by means of kind of simplifying, and so we have the exact same as what we had before. We have the natural log of u plus c. Now, I really probably should have used a different u here. I should have used a different letter, because I don't want you getting confused and thinking that u is the same as the u in the first question. It's not. You'll see that from where I define it here. So we do get the same integral out, but here we have a different value for u, and so essentially we do the integration, so we get natural log of absolute value of u plus c, and then we just substitute our value for u in there, which is this. And so this is the final answer. Amazing. Okay, cool. Now we move on to part 2 of question 1. And this is saying use a substitution. So we're not given a substitution this time. We have to figure one out for ourselves to find this integral, which looks a little bit more nasty than the ones we had before, and this integral. Okay, so I'll just scroll down to where I did my working. And so this is the first integral that we have to work with, this one here. Now what you can actually notice, and it's kind of like a little trick here, but what you'll notice is you can actually set u equal to the denominator in this integral, should I say. If you compute the differential of the denominator here, you can expand it out, perform the differential of different parts here, simplify, and we get this answer for du by dx. And what you'll notice is that's almost exactly the form that's on top here. And so that would cancel with that, and then you're quite simply left with this beautiful integral here. And so the important part of this question was just spotting that if you were to take the denominator, compute the derivative of that, it's essentially the same or almost the same as the numerator. So as before, we compute this integral, we get this response, we get this output for this integral, and then substituting u back into here, we get this lovely form of the answer here, and not forgetting c, of course. So amazing, that's the first integral. Now the next integral is this one here. So the first thing that I wanted to do was, we have a lot of sine and cosines here. And like with most integrals, what I like to do is try and simplify them into something that we've had previously. So in the previous questions we had tans, we had cots, and so obviously we know sine and cos, we can make tans and cots out of them. So what I did was multiply the top and the bottom by 1 over cos x to the power 4. And the reason I did that is because when you multiply them and simplify, you get this relation here. Now you might look at this relation and think, okay, this is looking a little bit similar to what we had previously. In fact, very similar. The only difference is we have an extra squared around here. And so what we can do is, well, we know that we took u as this value last time, and so we can do that again. We can take u as this denominator without the square, and then when you perform the differential of that and do everything again, we can find this, except u is just squared. And so we do exactly what we did in the previous question, which we already know the answer was 1 over 2u, the integral of that du, but obviously here we've just got an extra square, so we have an extra square here, and yeah, that's the integral there. And again, all we do is we compute this integral and substitute our value for u into here. Amazing. So yeah, that's the answer for the final part of question 1, and that's all the working that goes into question 1. I thought that was a really nice opening, introduction question. There's obviously tricks and things that you have to know about trigonometry to help with this question. I think otherwise, the first question's not too bad, the first part, because you're told how to substitute it in, so this is almost nice, but everything from then on you have to notice little tricks here and there. And I think that's one of the things that is very different between A-levels and then step papers for going to universities like Cambridge, is there's a lot of little subtleties that you don't really realise. And obviously watching this video you might think, oh, that's very intuitive, but that's why I encourage people to go and try these problems for themselves, because on this series of the hardest mathematics courses in the world, I've had a lot of debates in the comment section behind, well, which is actually the hardest. And so, I think I encourage everybody to try out a variety of different exams themselves and, deduce that for themselves. My kind of idea behind this is just, to show you how cool maths is and where it crops up in exams all over the world. Okay, the next question I decided to tackle was one of the later questions, and it's question number 8. And the reason I chose this question was because there's a little proof by induction in there, and that reminds me of one of my A-level maths teachers, Mr. Willen, who him and my other A-level maths teacher, Mrs. Davru, both of them are essentially the reason that I went and studied maths at university, because they were just so passionate about teaching and infused this excitement in me about maths. And it's one of the reasons why I do my YouTube channel, because I saw what an influence they had on me and what they continue to have on me, and I'd love to be that person for somebody else as well who may consider a career in mathematics. Anyway, back to the proof by induction. That's why I chose this question, because love a bit of proof by induction. So the question itself says 2 sequences are defined by a1 equals 1, b1 equals 2, and for n greater than or equal to 1, we have these relations here for an plus 1 and bn plus 1, and we're asked to prove by induction that this holds for all n greater than or equal to 1. Okay, so as with any proof by induction, we set up the first case, which is we want to check that this holds for n equals 1. So we want to check that this holds here for n equals 1. And so we can do that because we're told that a1 is 1 and b1 is 2. And so all we do is we substitute a1 into there, a1 into there, b1 into there, b1 into there, which is what I've done here. Substitute the values that we're told for those values into here, simplify, and essentially what we find is that 1 equals 1. So the left-hand side equals the right-hand side, so therefore the base case of n equals 1 is true, and so that holds. So that's the first step in the induction. Now, The second step in the induction process is we assume that this holds for n equals k. And so all we do is we substitute k for where n is. So we've got little n's in here. We just substitute k into there. Amazing. Now, point number 3, we want to, and I probably should have underlined this, so I'll just do that now. But point number 3 is, well, now we've said that this is true, we want to check that it holds for n equals k plus 1. So we're looking at the k plus 1 situation. So let's write this out for n equals k plus 1, which is what we have here. Now you can feel free to pause the video and take a look at the kind of this whole section here. Essentially all I do is I take this, which is what we've substituted the n equals k plus 1 into, and we're told these here. So we're told, you know, what an plus 1 equals, and we can also do the same for bn plus 1. So we know that they're equal to these, so we just substitute k into here, and so we would get a k there and a k there, k there, k there, and yeah, substitute those in. So we know that ak plus 1 from this relation here is ak plus 2bk, just substituting n for k in here, and so we get that there. And then for, let's say, bk plus 1, we know that's going to be 2ak plus 5bk, then substitute that in for where bk plus 1 is, and so you end up, this simplifies to all of this here. You can expand it out, and what I did was I expanded it out and then I collected terms. So I said, okay, well, let's look at all of the ak squared terms, and so we had 1. And then I said, let's look at all the ak bk terms, and we had 2. And I said, let's look at all the bk squared terms, we had -1. So we can rewrite all of this mathematics here into a really nice format, which is this here. And what we can deduce from that is that this here is this here. And we know that we've assumed it's true for n equals k. So this equals 1. So we can say that this equals 1. So therefore what we've deduced is the n equals k plus 1 situation says that this equals this, which therefore equals 1. And so we've proved by induction that, yeah, it holds. So therefore by induction, this does equal 1 for n is greater than or equal to 1. Now I should have mentioned actually we had n is greater than or equal to 1, and so when we did the base case here, that's why we check that n is 1. Obviously if it was n is greater than or equal to 0, then we'd want to check n equals 0 as the base case. So yeah, just forgot to mention that there. But yeah, that's essentially the first part of the question. Now the second part of the question, well, I say that's the first part. The second part is part I of the question. And so it says, let's see n equal an over bn. We want to show that this holds. So let's just focus on this first part here, because then it says and, so let's just focus on this first. So this question is quite interesting really, because when you look at questions, you often kind of try and see if there's anything that what you've done previously will help with this. And so we have Cn equals an over bn, and so you might naturally think, well, let's look at what an was in the previous question and see if we can deduce something from that. But actually, we can just use proof by induction again for this, and it's really, really nice. So we're going to prove this holds by induction. So again, we have number 1, which is the base case, and we say n is equal to 1. Well, what does this become when n equals 1? It becomes, that should actually say, that should be a 1 there. Let me just change that. That should say 1. So b1 for this case here is greater than or equal to 2 multiplied by 5, 1 minus 1. And obviously 5 to the 0 equals 1. And so I have no idea why that's a 0 there. That should be a 2. Excuse my error there. But essentially what we've said is b1 is greater than or equal to 2. And by the definition of sequences, we're told that they're greater than or equal to 0. So yeah, this holds. So we know that base case holds true. Amazing. Now, second case, obviously, second part is just to assume that n equals k is true, and so we get this formula here. And then we consider that n equals k plus 1 case. We know from the earlier part of the question that this holds. And so we can substitute the value for bk for this, which is what we do there. So essentially we just substitute bk in for this, and therefore we have this formula here. And then quite rightly, because ak is a sequence, that's always going to be greater than or equal to 0. And so we can say that this is always greater than or equal to 2 multiplied by 5 to the power k minus 1. And so by induction it holds. Now it's saying we want to use star. So star was what we deduced before. So this. Deduce star. From star, show that this holds. Okay, so now we're looking at how these sequences change for n tending towards infinity. Awesome. So where are we? So we're now, this is the part here. So let's walk through this. So we are told this, start the question. We know that Cn equals An divided by Bn. I rewrote out what our star equation was just to remind us. And we can do some manipulation on this. So what I did was I divided by Bn squared. So we get this here, this equation for star. Essentially it's star, but just rewritten in a different format. And so we have An divided by Bn squared. We have an An divided by Bn here, so we can substitute Cn because that equals An divided by Bn. We get this nice formula for star again here. Amazing. And now we're asked to basically show that Cn tends towards this value for n tending towards infinity. So let's look at what happens to this when n tends towards infinity. So firstly, we know, we've just proved by induction that Bn is greater than or equal to this value here. And so when we tend towards infinity for this, so when n tends towards infinity, 5n minus 1 is going to be 5. That'll tend towards 5 to the infinity, which obviously itself is going to tend towards infinity. So this is going to tend towards infinity. And so the right hand side, which is this here, is going to tend towards 0. Because if we have 1 divided by infinity, that will tend towards 0. So as n tends towards infinity, this term tends towards 0. So what we have is this here. And I should just say, because I've just rewritten out there, but I forgot to just say that that's actually equal to 0, because it is in this case, because the right hand side is going towards 0. So what we can do is note that, well, this is a quadratic formula. And what do? We essentially can find roots for this. So using the classic quadratic formula, we can find the roots for Cn. We find that it equals this. And because obviously the sequence is greater than or equal to 0, we deduce that we must take the positive part, not the negative. And so we end up with root 2 minus 1 as n tends towards infinity. And there we have it. We've answered that question and we've proved that this does indeed hold true. Now the very final part of this question says, show that Cn is greater than the root 2 minus 1, and hence this holds here, and then it says deduce this. So firstly we're going to show this. Alright, cool. So from before we had this formula here, didn't we? And this is just coming from this here. So let's look at, for just n generally, not as n tends towards infinity. So for n generally, we can essentially this and this would be a constant, and we can rewrite for Cn. So we can find the quadratic, you can use the quadratic formula again for Cn, and in doing that we find this here. Doing a little bit of simplification, we find this here. And because we have bn squared here, we already know that bn is greater than 0 because we've deduced it before and we've proved by induction that it is. And we've also just utilised the fact that Cn itself is also greater than or equal to 0, so we won't take the negative part here, we'll just take the positive. So yeah, so I think that's the first part. Yep, so we've just done the first part, which is this here. And now we want to show this. Okay, so how are we going to do this? So we have this. In fact, that should say just greater than. Excuse my math error there, but we know that Cn is greater than this. We've just shown it. So what we can do is take this form here, so 2 over Cn plus 1, and make an assumption about it. So 2 over Cn plus 1, 2 over Cn plus 1, well, we know that Cn is greater than this, so we can rewrite it like this and say this is less than this here. And again, simplifying, we can just cancel the 1's out there, get this value. We know we can rewrite 2 over root 2 as the same as this, and therefore it's less than root 2. This is less than root 2, but we also know from this here, just by rewriting, that root 2 is less than Cn plus 1, and so we can essentially use the fact that this holds and that this holds to write that these inequalities here hold. And there, we answer that part of the question. Cool, so we've done the first part, which is all of this. Now we want to deduce this. All right, so let's think about how we're going to go about doing that. So we want some numbers in here. We probably want to plug some numbers in because we have actual numbers itself. So what you do is basically just substitute in different numbers. So we know that A1, that should say A1, equals 1 and B1 equals 2. So we can just substitute into C1 to see what that is. We get half. Now because we have these, we know that we can just substitute A1 into here. So that can be 1, that can be 1. So A1 plus 2B1, and that'll give you A2. And so you can do that and iteratively do that, which is what we do, by substituting in the numbers here. And we can find them. So we find that A2 is 5, B2 is 12, therefore C is 5 over 12, A3 is 29, B3 is 70, so C3 is 29 over 70. And what we're wanting to do is every time we iterate, we're wanting to look for numbers that we can substitute into here, so values for Cn that will give us what we're told in the question, which is this. And when you iteratively do that, what you'll find is for A3, B3, and therefore C3, we can substitute C3 into this here. We get this form of it here, which reduces to this form here. And that is the answer. So we've deduced correctly that yes, that does hold, and it holds for when we have C3 in there. Cool, that was question 8. I really like that question. Again, I like the induction, but I also like the pulling different aspects from the question to get it to work. And yeah, there's a lot that you had to think about there. So yeah, nice question.
We've definitely seen a lot of difficult maths in this exam so far, and a lot of it requires little tricks here and there, but most importantly, being able to remember important mathematical concepts. And if you're looking to improve your mathematical memory, or even just your mathematics in general, I would highly recommend checking out Brilliant.org. Brilliant is a platform where you learn by doing, with thousands of courses in mathematics as well as science, including astrophysics, which are some of my personal favourites, data science, programming, and even AI. Each lesson is filled with hands-on problem solving, and this allows you to play with concepts, which is a method that's proven to be 6 times more effective than simply watching lectures. Brilliant allows you to build knowledge little by little each day. As a bit of a tech nerd myself, one of my favourite courses is their course on how large language models work. To try out this course, as well as everything else that Brilliant has to offer for free for a full 30 days, visit brilliant.org/Ellie Slighto or click on the link in the description, and you'll also get 20% off Brilliant's annual premium subscription. Now let's dive into the mechanics section of the exam.
Now, because I am an applied mathematician, I do quite like mechanics, and so for the last question of this video, I have selected one of the questions from the mechanics section. It's the last question in the mechanics section, so yeah, there's a little bit of work to go into it, but let's look at it now. Okay, so this is the final question. It's question 11 from the mechanics section, and yeah, let's take a look at it. I'm going to speed run through this because I realise I've spent a lot of time talking in this video, but feel free to pause and look at my working out at any point. Yeah, cool. So we have a diagram here, so this helps us visualise what's happening, and just ignore the different kind of forces I've added onto here. We'll get onto them in just a moment. So the question says a plane makes, and I'll just zoom in, A plane makes an acute angle alpha with the horizontal. So we can see that here. And it says, I'll just zoom out so we can see both. It says a box in the shape of a cube, which obviously we see here, is fixed onto the plane in such a way that 4 of its edges are horizontal and 2 of its sides are vertical, which is what we see in this diagram. A uniform rod of length 2L and weight W rests with its lower end at A at the bottom of the box and its upper end at B on the side of the box, as shown in the diagram below. So we see that, so this is the rod here, top end is at B, bottom end is at A, if you can see that that's an A there. And we're told, what we're told about it, that its length is 2L, so this is L, and we're told that we have a weight, W. Then it says, the vertical plane containing the rod is parallel to the vertical sides of the box and cuts the lowest edge of the box at O, so we see that here. The coefficients of friction between the rod and the box at the 2 points of contact are both tan gamma, where this is the range for gamma, and it says the rod is in limiting equilibrium with the end at A on the point of slipping in the direction away from B, so this is going to slip this way, away from B, and at the end of B, slipping towards O, so this is going to be slipping towards this way. Okay, given that alpha is less than beta, we want to show that beta equals alpha plus 2 gamma. So, there's a lot going on here. Now, obviously, there is a little hint, but one of the first things I always think about doing with mechanics questions is just looking at the forces. So the first thing we want to do is look at the forces in this setup, and then we can use those forces to, as it says in the hint, we may find it helpful to take moments around the midpoint of the rod. We've got a lot of information here, so let's go through it. So firstly, we have frictional and reactional forces. So if we look at the situation of what's happening at A, we know that the frictional force is acting this way because we're told that the rod is slipping this way. We obviously have a reaction force here. We know that frictional forces are given by the coefficient of friction multiplied by the reaction force. So F of A equals mu multiplied by RA. So mu here I've called as the coefficient of friction. We're told in the question here that the coefficients of friction are tan gamma, and so we can just substitute mu for tan gamma here, and so we get these two equations for both A and B for the frictional and reactional forces. So amazing. Now what we can do, we obviously have these forces that we can see and we know we have these two equations, but we want to look at how these equations are acting in different directions. So firstly, we can look at parallel to the slope. So if we look at parallel to the slope, which is this one here, we can say, well, we have F of A, we know that's already parallel to the slope. So F of A, which equals RA tan gamma, which is what we have here. Now we also take the effect of the weight of the rod, which is what we can see denoted here. And by some geometry, feel free to pause the video and test out the different geometry elements for yourself, but I'm going to speed run through it. In this question, we have W sine alpha, which is also the force parallel to the slope, and we have RB, which you'll notice here is parallel to the slope. Amazing. Now we can do the same for the perpendicular, and immediately we can see we have RA, we also have F of B, and we will also have a component from W again, and so we have F of B, which we see here. So F of B plus the perpendicular component from W, so W cos alpha, equals R of A. Okay, so now we've looked at the forces in both the perpendicular and the parallel to the slope direction. We can basically take these two equations here and we can eliminate W from them. And so when we do that, we find this here. So all you're going to do, and feel free to pause the video and attempt this yourself, take these two equations, eliminate for W, and what you find by using a bit of elimination here and also the double angle formula for tan, we find that RB equals tan of alpha plus gamma multiplied by RA. So this is a key point to get to in the question. Amazing. So we have this formula for RB related to RA. Amazing. Now, in the question it says, you may find it helpful to take moments around the midpoint of the rod. We know that the rod itself is 2L, so the length is 2L, and we can, take moments. So what I've done here is I've drawn a very funky looking diagram about taking the moments. This was just when I was kind of brute force going through it. And so let's just take a look here. So we know that moments are force times distance, and essentially all we're going to do is we're going to look at the force in the direction at B at this point, and the force in the direction at A here, which is perpendicular to the rod itself. And when you do that, you can find the force in that direction and then multiply it by L, which is what we've done here. So you'll see that L is multiplied by everything here, and essentially balance the forces on either side of the rod, which is why we have an equal sign here, because we've balanced those forces. We can just kind of running through this, because again I've been talking for so long, we can simplify this and essentially arrive at this relation here for in relation, that shouldn't have an L there, just realised that should not have an L. We have this relation here for RB and RA, again in terms of tan beta and tan gamma. Now we know from the previous part of the question we have a relation for RB to RA already, so we can substitute that into here, and when we do that we can rearrange, we can do some kind of nice little mathematics here, which feel free to pause and take a look at, and we find when we do that we can essentially eliminate RB and RA from that equation, so from this here. And when we do that we find that tan beta is given by this funky little formula here, but again by remembering the double angle formula for tan, this funky little equation here can be written as this here. And so what we find is tan beta equals tan alpha plus 2 gamma. Now obviously we have tan on both sides here, tan of something, and so we can deduce from this that beta must therefore equal alpha plus 2 gamma plus n times pi, because obviously that's the repeated period for tan. And by looking at kind of what we've been given in the question, we're basically told that alpha is less than beta. So we know that already. So this is less than beta, perfect. But we also know that beta is acute, so it's less than 90 degrees. And so therefore from this, since alpha is less than beta and beta is less than 90 degrees, we essentially take the case for when n equals 0 here, and so beta equals alpha plus 2 gamma. And that is the final answer. That was the video today. I hope you enjoyed it. If you did, then please like, subscribe and comment. Thank you so much for watching, and I'll see you all in the next one.